Welcome to this second video of a playlist about carbon dioxide. In this video I'll compare the reactivity of CO2 with that of two closely related heterocumulines, methyl isocyanate and ketene. As usual, you can find a PDF version of the slides under the Community tab of my channel. Carbon dioxide is quite unreactive and non-toxic, while isocyanates and ketene react violently and irreversibly with nucleophiles, including the proteins in our lungs, and are therefore very toxic. Methyl isocyanate is produced on a large scale as intermediate for methyl carbamates, an important class of insecticides. This reagent killed about 8,000 people in the 1984 Bhopal accident in India. Ketene is also manufactured on a large scale, but must be used immediately after its generation because of its high reactivity. It is either dimerized to diketene or used to prepare acetic anhydride, organic acetates, or a number of other products. If we compare the structure of these three compounds, this increasing reactivity when going from CO2 to ketene is not what we would anticipate. In carbon dioxide, two electrophilic oxygen atoms are pulling at the same carbon atom, and we would expect it to be more reactive than isocyanates or ketenes. Carbonyl compounds, for instance formaldehyde, are more reactive and electrophilic than imines, and imines are more reactive than simple alkenes. So why is ketene more reactive than methyl isocyanate, and both more reactive than carbon dioxide? In fact, electrophilicity refers to relative reaction rates and is thus a kinetic property. In a recent article, the electrophilicity of various heterocumulines toward carbon nucleophiles was measured, and carbon dioxide turned out to be more electrophilic than phenyl isocyanate. It reacts faster with nucleophiles because the activation barrier is lower. Because of the high stability of carbon dioxide, however, its reaction with nucleophiles is often endothermic and reversible. Here I've sketched the calculated energy profiles for the reaction of phenyl isocyanate and carbon dioxide with deprotonated malononitrile. The reaction with carbon dioxide is faster because of its lower activation energy, that is, the energy of the first transition state is lower than that of phenyl isocyanate. The overall reaction with carbon dioxide will not proceed, however, because the final product has a higher energy than the starting materials. The main driving force of these reactions is the final proton migration to nitrogen and oxygen. Because nitrogen is less electronegative than oxygen, deprotonated amides are more basic than carboxylates, and the reaction of phenyl isocyanate is therefore more exergonic than that of carbon dioxide. More about this later. With the aid of standard enthalpies of formation, I've calculated here the standard reaction enthalpies for the hydration of cumulines, without taking into account solvent effects. While the hydration of CO2 is endothermic, reaction of isocyanic acid, ketene, and even alene with water is clearly exothermic. These calculated enthalpies also conform to the observed reactivities. The hydration of carbon dioxide is endothermic and does not proceed readily, while isocyanates and ketene react violently and exothermically with water, although sometimes a catalyst is required. Similarly, carbamic acid, the product of the second equation, readily fragments into carbon dioxide and ammonia at room temperature, while urea or acetamide require at least 150 degrees Celsius to begin to decompose. Carbon dioxide is just a very stable compound, and the conversion of its carbon atom from sp to sp2 hybridization is energetically unfavorable. Reactions with methanol follow a similar pattern. Here, the addition to carbon dioxide is exothermic, but only slightly. One unique characteristic of heterocumulines is their tendency to oligomerize. Ketene, for instance, readily dimerizes exothermically at room temperature to diketene. No such dimerization of carbon dioxide has been observed, not even at high pressure. Alkyl isocyanates trimerize exothermically and irreversibly if a suitable catalyst is added. The cyclic trimer of carbon dioxide, however, was thermally unstable and fragmented already at -40 degrees Celsius. Thus, all these results show that CO2 is remarkably stable and unreactive when compared to isocyanates or ketenes. Before starting with our cumulene comparison, a few words about carbonyl groups. Carbon-oxygen pi bonds are similarly strong as CO-sigma bonds and carbon-carbon sigma bonds. CC-sigma bonds are usually much stronger than CC-pi bonds. For example, the CO-pi bond of formaldehyde has 82% of the strength of the CO-sigma bond of methanol, while the CC-pi bond of ethylene is only 72% as strong as the CC bond of ethane. This is the reason why aldehydes, carboxylic acids or carbon dioxide add water only sluggishly and reversibly. Depending on the other two substituents, the energy gained by forming a new CO-sigma bond can be less than the energy required to cleave the CO-pi bond. This is clearly the case for the hydration of carboxylic acids or carbonic acid, the last two equations on this slide. These hydrations are strongly endothermic and are not usually observed. As a general rule, if the substituents at a carbonyl group have lone electron pairs, the electrophilicity of the carbonyl group decreases. If the substituents are electron withdrawing and do not carry lone electron pairs, then the carbonyl group becomes more electrophilic. Thus, trifluoromethyl ketones or chlorinated aldehydes often form stable hydrates or hemiacetals, as in the first two equations on the slide. Also, while carbon-centered radicals tend to add smoothly to CC double bonds, because the newly formed CC-sigma bond is stronger than the cleaved CC-pi bond, carbon-centered radicals do not usually add to carbonyl groups. So, why is carbon dioxide less reactive than methyl isocyanate or ketene? Here I've listed some of the physicochemical properties of these compounds and of acetone for comparison. As expected, there is a correlation between the overall dipole moment of a compound and its boiling point. IR spectroscopy shows that in carbon dioxide the CO bonds have a higher resonance frequency and are thus stronger than in isocyanates or ketenes. All three cumulenes absorb at a much higher frequency than ketones or aldehydes, because the central carbon atom is an sp hybrid. sp orbitals have a lower energy and more s character than sp2 orbitals, and the CO-sigma bond between an sp carbon and oxygen is therefore shorter and stronger than between an sp2 carbon and oxygen. This shorter sigma bond in turn leads to a better overlap of pi orbitals and thus to stronger pi bonds. The blue lines in this sketch represent the sigma bonding and antibonding molecular orbitals formed from an sp2 carbon atom and sp2 oxygen, and the green lines those same orbitals from an sp carbon and sp2 oxygen. The energy gain, as indicated by the red arrows, is smaller for the sp2-sp2 combination because of the larger energy gap between the carbon and oxygen sp2 orbitals. The larger the energy difference between two orbitals, the smaller the energy gained by combining these orbitals. Let's compare the resonance formulas. Often, the more and the more stable the resonance formulas of a given compound, the higher its stability. As a reminder, resonance formulas only describe the delocalization of electrons for a given molecular geometry. So, the atomic nuclei must remain at exactly the same position for all resonance formulas. These should not be mistaken for tautomers or valence isomers. Here I've sketched only those formulas accessible by moving two electron pairs at a time. The electron delocalization in carbon dioxide can be described by three low-energy resonance formulas. In the left and right ionic formulas, there is an additional electrostatic attraction between both oxygen atoms, what could cause a further strengthening of the bonds. Importantly, in all three resonance formulas, the central carbon atom maintains its sp hybridization and the corresponding linear structure. This is not the case for isocyanates, however. Here, again, we have three stable resonance formulas, but with a different nitrogen hybridization in each of them. The right-hand formula would require sp hybridization of nitrogen and a linear structure. Thus, the hybridization of nitrogen in isocyanates is neither sp2 nor sp, but somewhere in between, what is the reason for the large CNC angle. Therefore, resonance stabilization by electron delocalization in isocyanates is not as effective as in carbon dioxide. Still less stabilized are ketenes. Here, the formula on the right with a negative charge at oxygen would imply a divalent central carbon atom. Carbenes have only 6 valence electrons and are highly reactive, unstable electrophiles. Compounds where electron delocalization from carbon to oxygen leads to a carbene tend to be highly reactive and unstable. Acyl anions, for instance, can be formed by deprotonation of aldehydes or from polar organometallics and carbon monoxide at low temperature. Because of their carbenoid resonance destabilization, acyl anions tend to dimerize and to yield complex product mixtures. Other unstable intermediates include deprotonated propiolic esters, methylated acrylates, and some vinylic carbocations. All these are difficult to generate and tend to yield unexpected products. A further parameter destabilizing ketene is its basicity, compared to that of isocyanates or carbon dioxide. The left resonance formula of ketene, with a negative charge at carbon, is much more basic and energy-rich than the corresponding formulas for isocyanates or carbon dioxide, because of the lower electronegativity of carbon compared to nitrogen or oxygen. So, these resonance formulas suggest that carbon dioxide is better stabilized by electron delocalization than isocyanates and ketenes. As suggested by the resonance formulas and the energy profile of the reaction of phenyl isocyanate with malononitrile, one parameter that may be decisive for the reactivity of heterocumulines is their basicity. pKa values of reactive compounds are difficult to measure, and it's easier to compare proton affinities. These are the calculated reaction enthalpies of protonation in the gas phase, without any solvent effects. The values given here show that CO2 is a weak base only, while ketene is a much stronger base, with almost the same proton affinity as ammonia. If we replace the cationic CO group by a cyano group, the resulting isoelectronic compounds are isocyanic acid, cyanamide, and acetonitrile. In water, isocyanic acid is a weak acid, while cyanamide will only be deprotonated by strong bases like sodium hydroxide. Acetonitrile is an extremely weak acid, and no stoichiometric deprotonation can be achieved in water. Because of the higher proton affinity of ketene, during its hydrolysis a relatively high concentration of protonated ketene will be formed as intermediate, which is a much stronger electrophile than unprotonated carbon dioxide. In fact, most reactions of ketene with protic nucleophiles can be catalyzed by acids and proceed by intermediate formation of an acylium cation. The alternative intermediate would be the anionic addition product of hydroxide to the cumulene. This is the preferred pathway for carbon dioxide because of its lower basicity and more electrophilic carbon atom, if compared to unprotonated ketene. Most nucleophilic additions to carbon dioxide are catalyzed by bases, as we'll see in the next videos of this playlist. Thus, ketene is more reactive toward protic nucleophiles because protonation of ketene is fast and extensive, and because acylium cations react faster with nucleophiles than neutral carbon dioxide. I had some helpful discussions with 2 specialists, so thanks for that. The next video of this playlist is about the preparation of carboxylic acids by carboxylation at carbon with carbon dioxide and carbon monoxide. I've included examples of carboxylation by substitution of hydrogen, halides and sulfonates. See you!